Okay, yeah, thank you everybody for tuning in. This is the last one of these webinars from the winter-spring season. We're going to be bringing up the topic at the meeting next week. Hopefully most of you will be there. And we're looking to see if people feel like this is a useful effort. If we want to continue next year, maybe propose some themes which we can organize these talks around. So have that in mind between now and next week. For today, we have Tom Haine, and he's going to be talking about some conceptual constraints on polar MOCs, which seems like a nice way to close out our topic area of influences of freshwater on the MOC.
Okay, so I'm interested in the polar end of the meridional overturning circulation, particularly in the Atlantic. I think about the subpolar gyre, the Nordic seas, and the Arctic Ocean. And I've been thinking about conceptual models for how that might work. And I want to share that with you today. Constraints is perhaps overstating it a little. I have a constraint. I think it's useful, but what I'm going to describe is essentially incomplete. I'm interested to hear your feedback about where one might go next. So to set the scene, let me show this beautiful figure from Takamasa Shibuchi's paper in 2012, and it is a figure of Arctic gateways. So you go Davis Strait, Fram Strait, Barents Sea opening, Bering Strait from left to right, and its potential temperature and salinity measured from ships and maybe some moorings as well. And you can see that, for example, in the Fram Strait, the water on the eastern side at the surface is warm, maybe 8 or 10 degrees C, and salty in excess of 35 salinity. And then on the western side of the Belgica Bank, it is cold, close to the freezing point, and fresh, maybe 30 or 32 salinity. And that pattern you can see in the Barents Sea opening as well, to a certain extent. You can also see it in Davis Strait. On the western side, you have cold, fresh water, and on the eastern side, you have warm, salty water. And if you look at Takamasa's velocity section, so in this paper, he computed an absolute geostrophic velocity across these gateways using an inverse method, then you can see, as everybody knows, that the warm salty water is flowing into the Arctic and the cold fresh water is flowing out of the Arctic. So in particular, in the Fram Strait, this is the East Greenland current, partly over the shelf break, partly over the continental shelf, the cold, near freezing fresh water. This is the imprint of the West Spitsbergen current, warm, salty, originally Atlantic water flowing into the Arctic. And you can see the same thing in Davis Strait. To a certain extent, you can see the same thing in the Barents Sea opening. So the climate system is interesting in the following respect. The tail end of the overturning circulation towards the pole consists of warm, salty surface water flowing polewards. The climate system then modifies that water. It extracts heat. It adds fresh water ultimately from the atmosphere. And what is returned equatorwards consists of freezing point fresh water, which is in the East Greenland current at the surface. It consists of sea ice, which is also flowing in the East Greenland current. That's not shown on these diagrams. And it consists of a deeper, slightly fresher, cooler water mass, which is down here. So it's kind of below the East Greenland current, and that's called intermediate water. So if you look at a TS diagram, so the TS diagram here is for Fram Strait. It's not the same data that Takamasa is plotting on the left. It's from a Poseidon occupation of Fram Strait. Then you can see these water masses quite clearly. So the Atlantic water is the warm, salty stuff here. That's flowing in the West Spitsbergen current into the Arctic. And then the water masses which are flowing out on the western side are the East Greenland current, which is near the freezing line and extends to very fresh salinities. And then these dark grey dots here are what's called intermediate water. So this is slightly cooled, slightly freshened, slightly denser version of Atlantic water, and that sits beneath the East Greenland current here. And then deeper than that, there are abyssal water masses, which are right down here, the most dense waters, which I'm not going to talk about today. So, of course, this is relevant for the Atlantic meridional overturning circulation in the open Atlantic because essentially this exchange occurs at the Greenland-Scotland ridge as well. In other words, there's warm, salty Atlantic water flowing into the Nordic seas. What the climate system returns is cold, fresh, near freezing point East Greenland current on the East Greenland shelf, some sea ice, and then intermediate water, which is a cooled, freshened version of Atlantic water, which will ultimately feed the overflows and form the lower part of the North Atlantic deep water. It also is essentially the mode of exchange in the southern polar end of the overturning circulation. So if you do a TS diagram for the Weddell Sea, for example, you see essentially this same kind of structure. So the water mass that's warm and salty there is circumpolar deep water. Of course, details are different because the CDW has to negotiate under the Antarctic circumpolar current. It then rises to the surface. It loses heat to the atmosphere. There's freezing, and then what's returned are two modes, essentially a cold, fresh mode, sea ice, and then a dense water, which is saltier or maybe slightly fresher and colder, and that would be forming the Antarctic bottom water. So what the climate system does to the warm, salty end of the overturning circulation is convert it into an alpha overturning piece, which is the intermediate water. So that is deeper, it's denser, and it's denser principally because of its temperature. And what we call a beta overturning piece, which is the East Greenland current, and you can also think of the sea ice as being a piece of that too. So that is driven, its density is driven principally by salinity. And both of those then go on to influence the AMOC in lower latitudes. So I'm interested in particular in what sets the properties of the outflowing cold, fresh East Greenland current. And so you see these symbols here. These are predictions to the end points. So there's a very sharp cutoff of salinity here for the East Greenland current, which is a little more than 34.5. And then here there's another relatively well-defined minimum in salinity. And then the water is both warmer and fresher over here, and also in the Atlantic water it's warmer and somewhat fresher, because this is a section that was taken in summer. So the fact that there's been seasonal melt and warming and you've pushed everything towards warmer, fresher water is not particularly surprising. So I'm interested in figuring out what sets these properties of East Greenland current. You can see that there's a very sharp cutoff in salinity, and maximum salinity in particular. You see the same thing in the Weddell Sea. Okay, so I'm going to talk about a very simple conceptual model which describes what I think are the key processes. It is an upper ocean mixed layer model where Atlantic water, which is warm and salty, is interacting with sea ice and the atmosphere. So the warm, salty Atlantic water is losing heat both to the atmosphere and to melting sea ice. And that forms a surface layer which is buoyant. It's called the polar surface layer. It's cold and fresh. And a key element of this model is that the sea ice is formed remotely. For example, it might be formed on the Siberian shelves and then is advected into the place where this conceptual exchange is occurring, which might be, for example, in the Eurasian Basin. So you've got northward flowing warm, salty Atlantic water hitting equatorward flowing sea ice, which has come across the pole and the transpolar drift, for example. Okay, so we're going to talk about the thickness of this polar surface layer, its temperature, its salinity. There's heat loss, a fraction phi of that is going to melt ice, we're going to vary phi. The rest is going to the atmosphere. There's some wind mixing. The layer might be deepening through entrainment. And then we have to take account of the fresh water and heat fluxes associated with the melting, which is M. So here's a set of equations which shows those fluxes. So Q is the total heat lost from the polar surface layer. And that consists of the sum of two pieces, a piece going to the atmosphere, which is 1 minus phi times q, and then a piece which is going to melt. So subscript I means the ice, so you've got a melt rate of ice, its density, and then this is the effective heat capacity, which consists mainly of the latent heat capacity, and then you have to cool the polar surface layer to the freezing point and then warm up the ice from the ice temperature to the freezing point. Both these terms are relatively small. So that's the heat flux, and then there's a freshwater flux associated with the melting of the ice. There's no freshwater exchange with the atmosphere. It's all coming from ice melt. And we're thinking about this in the winter season. So there's no solar radiation, and we're simply cooling the layer as the winter proceeds. So M is the M sub I is the mass loss of ice. M is freshwater flux, and you can compute that if you know Q and phi, and then you have the effective heat capacity of the ice down here in the denominator. Okay, so those are the fluxes of heat and fresh water and ice. And then here on the left are the equations which govern the evolution of the properties of the layer. Its thickness H, its temperature T, and its salinity S. So the thickness will change because you're in training. So positive WE means it's deepening. That is by far the largest term. There is a small change in the layer thickness because you melt ice as well, but that's relatively small. You might only melt a meter or two over the whole winter season. And then for the heat equation, you're entraining water from below if you're deepening, and the temperature difference between the polar surface layers delta T. So it's warm in the Atlantic water layer, cold at the surface. So in entrainment, as you deepen, warms the surface layer. And then this is the total heat loss, either to the ice melt or to the atmosphere. And then for salinity, same kind of thing. You entrain the salty water, and then here's the source of fresh water from ice melt. And then to close these equations, we need to compute these quantities. We need to have some parameterization for the entrainment rate, WE. And this formula here is a simple, convenient form. It's from Cato and Phillips. And it says that the entrainment rate is due to a competition of two effects. One is wind-driven mixing. So this will be turbulent kinetic energy input by the wind. The effectiveness of that at driving entrainment goes inversely as the layer thickness. So as the layer deepens, it becomes less effective. And it goes inversely as the density contrasts between the polar surface layer and the Atlantic water. So it's harder to entrain water across the base of the mixed layer if there's a big density jump. And competing with the wind-driven deepening is the buoyancy term. So B here is the buoyancy flux. It consists of two pieces, one due to heat, one due to fresh water. So alpha and beta here are the expansion and contraction coefficients for T and S. And then it's written in terms of a buoyancy flux. And the buoyancy flux can have either sign, depending on the competition between heat loss and freshening. And if the layer is gaining buoyancy, in other words, B is positive, then this thing epsilon is equal to 1, which means that the buoyancy gain is quite effective at opposing the deepening of the layer by mixing from the wind. If, however, B is negative, in other words, the layer is getting less buoyant, more dense, then the efficiency at deepening from convective overturning is relatively small. So this is a 5% efficiency at epsilon when the layer is getting deeper because of convective overturning. So in this set of equations, we use the TEOS10 equation of state, and let's compute the delta rho here. And you can see that that's one source of nonlinearity, but there's multiple other sources of nonlinearity here, like these products, WE times delta T, and then 1 over delta rho, and 1 over H here, and so on. So it's a set of coupled nonlinear ordinary differential equations. And what we've done is compute solutions to these for a range of parameters. And we've looked at the phi q space. So phi, remember, is the fraction of heat flux going to melting. If phi is 1, then all of the heat flux lost from the surface layer is going to melt ice. there's 0, then there's none. And then Q ranges between 0 and 200 watts per meter squared. So this is for heat loss. And we start with an initial condition, which is essentially a column consisting entirely of Atlantic water at about, I think in this case, it's 3 degrees C. Yeah, that's right, and a little over 35 salinity. And we integrate for the winter season, which is nominally 6 months. And we figure out the final salinity, final temperature, final depth of the layer, and the total ice melted. So, for example, if all of the heat flux is going to melt ice, then you would end up here, and your salinity would have dropped. It would have fallen in the polar surface layer. And for most values of Q, you would reach this blue phase here, which is the freezing point. So in other words, within the 6 months, you cool the surface layer to the freezing point. You melt ice, the salinity lowers, and you're melting, say, between 2 and 3 meters of ice in total. And then the calculation stops when you hit the freezing point. And in that particular case, what you find is that the depth of the layer does not change very much. So it starts off nominally at 50 meters, and it doesn't change its depth very much. If you starve the heat flux to the going to melt ice and push more and more into loss to the atmosphere, then things are a little different. So you melt less ice, your final salinity is higher. For a range of phi values, you still hit the freezing point, but then for certain values, once you're below a particular cutoff, then you no longer reach the freezing point within 9 months, within 6 months, and a couple of other things can happen. So on the next diagram, you can see that phi Q space split out into various different categories, which we call integration outcome. So this purple stuff here is freezing. So you reach the freezing point within the 6-month winter integration period. If you're in the cyan region, you're still melting quite a lot of ice because phi is quite large, but you haven't reached the freezing point because you've not integrated for long enough. In other words, you don't reach the freezing point within 6 months. You're at some temperature above the freezing point. If phi is small, so most of the heat flux is going to the atmosphere, not to melting ice, then for most values of Q, you do not reach the freezing point, and instead you destabilize the upper layer. Because in that case, you cool the upper layer off, but you're not making it buoyant by adding fresh water from ice melt. And so as you cool it colder and colder and colder, it reaches a point where it just becomes statically unstable and it would overturn. We stop the calculation before that happens, but in principle, what would happen is that the polar water would just then convex into the Atlantic layer beneath. That doesn't happen in the Eurasian Basin. Maybe it happens in the Greenland Sea where there's a little bit less ice to melt. So the fraction of heat going to melt ice would be lower. And then there's this intermediate region here, this green patch where the layer gets extremely deep. So if you go back to the previous diagram, it's this yellow final depth. And so once the layer gets more than 200 meters deep, I just stop the calculation because it's kind of become unrealistic. And so this is a case where you're almost balancing, you almost have zero net buoyancy input because you're cooling to the atmosphere, but you're also melting some ice and therefore freshening. And so the layer does not become unstable, but it gets very, very deep because it continues to entrain as time goes by and it never gets cold enough to reach freezing. Okay, so if you're thinking about this as a conceptual model to form East Greenland current water, then the relevant part of this space is the purple region, because this is water which is at the freezing point, and at the end of the winter, it hasn't got incredibly deep and it hasn't convected. So the properties of this purple region are the relevant properties if this model is going to be effective about talking to the East Greenland current properties. And if you go back, so the salinity of this region depends on phi, and it depends weakly on Q as well. And this diagram shows the final salinity against phi for actually all of the points in this purple patch. And so you can see as phi goes up and you melt more and more ice, then your salinity drops, it goes down. And then there is a particular limiting value of phi, which is a little less than 0.4 here, where you reach a maximum salinity, which is about 34.5. And that purple circle corresponds to this purple circle here. And that's the point which has the largest final salinity at the freezing point. It's for the highest Q value that we chose. Okay, and these dashed lines are predictions of both the minimum value of phi and the maximum value of the salinity from these formulae. So these black lines in my sort of integration outcome category diagram, we have analytic expressions for, and here are some of those expressions. So S1 is the final salinity. Well, actually, sorry, S1 is the final salinity regardless of your value of phi, as long as you're in the purple region. And then this vertical dashed line here is phi min. And when you stick phi min into this formula up here, then you get the salinity of this purple circle. So that purple circle is a little more than 34.5. It's this purple circle here on the TS diagram. So all of these experiments started with this Atlantic water at 3 degrees C, and then we use a range of phi and Qs, and we find that we will produce East Greenland current water, we would call East Greenland current water, in other words, at the freezing point, with a salinity which is less than this purple circle, which corresponds quite nicely to data. Okay, so all of that is kind of interesting. Hindsight is 2020. I think we understand more clearly what's going on now than when we began this process. So let me talk about that, and then I'll just wrap up. So you're starting with Atlantic water here. So actually there's a range of temperatures, not a very big range of salinities. So I showed you the case here. The parameter phi is unknown. Nature sets that through some process that is mysterious. But the direction in which this Atlantic water moves on the TS diagram depends on that value of phi. So for example, if phi was 0, there's no heat flux going to melting, then the properties of this point would just move vertically downwards. In other words, it would cool, but it would never change its salinity. Okay, well, that wouldn't give us an East Greenland current water because it would become statically unstable. If phi is equal to 1, then you'd end up down here for freezing point water, and your salinity would be about 33.5. That's this black line here. So you'd end up about here at about 33.5 if you started with Atlantic water at 3 degrees C. So the purple circle is this second black arrow. So for this range of experiments, you're going to end up with freezing point water that you would call Greenland current from this conceptual model with a range of salinities here. If you start with warmer Atlantic water, you're going to end up having to melt more ice in order to reach freezing point, and unsurprisingly, you end up with a fresher East Greenland current water. And so that you'd end up in this blue square down here. And as I said earlier, the stuff to the left and up is just seasonal warming and melting of ice from shortwave radiation in the summer. So I don't think that's particularly important. So this is a model which at least can account for aspects of what you see in the TS diagram. Now here's the part which is kind of interesting in retrospect. The limiting value of phi, in other words, you want to melt the minimum amount of ice, so it's phi min, and therefore have the saltiest product water at the freezing point, is along this black line, which is tangent to these isopycnals. So there isn't an isopycnal going through that point, but you can see the neighboring isopycnal. So that line, which is tangent to the isopycnal going through that Atlantic water point, will define the value of phi, which is minimum for you to produce a polar surface layer that does not overturn. If it's any steeper than that, in other words, if it's any more vertical, then it will end up making water which is denser than the initial water, and it would overturn and therefore will not be counted. So in retrospect, it's quite easy. You just simply take your Atlantic water point here and then take the tangent line for the surface density contour which goes through that point until you hit the freezing line, and that defines the maximum salinity of the water that you can make and call East Greenland current water in this simple conceptual model. Okay, so I just have a few final remarks. So the model is a model for the properties of the East Greenland current. But I think it's more generic than that because I think it also applies to the Southern Ocean and the Weddell Sea. And so I think that there are generic features of this which are relevant to any time you consider the polar end of an overturning circulation. It fits the data quite well, but I think that that's somewhat coincidental. Or in other words, I can modify, for example, my starting Atlantic water temperature in order to get a good fit with the data. I don't think the fit with the observations is particularly significant. I think the fact that you get this very sharp maximum salinity is more important. Now, Bert Rudels, for whom I have massive respect, has thought about this problem for many years, and he's published many papers on essentially exactly this topic. And he computes a similar salinity and a similar fraction of heat going to melting with the same goal in mind. Now, his formula for phi min is twice what I have. So he's got -2 alpha L over beta C S. However, he gets the same numeric salinity. And the reason for that, oh, hold on a sec. Sorry, can you come back in a minute? Thank you, someone's cleaning my waste paper bins. So Bert's formula is twice what I have, but he gets the same numeric answer because he chooses an alpha, which is half the value I pick. So alpha is a strong function of temperature. And in the numerical ODE solver that we use, we let alpha depend on the local temperature and salinity using TOS 10. Now, it turns out in my formula that the relevant alpha is the alpha at the starting condition. Okay, and this tangent line argument. Bert uses the average temperature. Well, alpha at the freezing point is about 0. So Bert's alpha is half of my alpha. And that's the reason his formula gives the same numeric salinity as mine does. He has some other arguments about the way in which phi is chosen by the air-sea-ice interaction, which I don't have time to go into, and I think probably not right in detail. Okay, so a couple of other final comments. The model is extremely simple. It emphasizes partial melting of remotely formed sea ice. Okay, so the sea ice is formed elsewhere, like on the shelves of Siberia. It's then advected by the winds into the place where it interacts with the Atlantic water, and there is incomplete melting of that ice. So in everything I showed you, I always had enough ice to melt. I didn't run out of ice. That isn't true in the Greenland Sea, for example. It might not be true in the Eurasian Basin in future, but those are the essential elements. And now here's the final remark about how this model is incomplete. If one wanted to construct a complete theory of why the polar end of the MOC takes warm, salty water and converts it into sea ice, the East Greenland current, and intermediate water, one would need to have other arguments about, for example, the properties of the intermediate water. So the intermediate water is formed presumably by mixing of Atlantic water with mode, which is not present on this salinity, this TS diagram, which is the continental shelf water, which is at the freezing point, but is in the place where there is net ice formation and therefore is salinifying, which is in the direction of this heavy black arrow. So it's sliding along the freezing point off to the right, and then that mixes with Atlantic water through some process to form intermediate water. What sets the properties of that or the balance between those two mixtures is unclear and would be necessary to have a complete theory. Okay, I welcome your questions.
Thank you, Tom, very much. To remind us for folks, before we go into Q&A, we'll take a few moments to answer questions for Tom. Raise your hand in the bottom left-hand corner, that way we don't speak over one another. I'm going to go ahead and take everyone off mute. If you're in a noisy place, please consider using the mute button on your phone or computer.
The conference has been unmuted.
So I saw we have a number of hands up. Mike, Paul, why don't we go ahead and go first?
Sure. So, Tom, you're talking about the outcome or the properties of the product water. Can you say anything about volumes or exchange rate in terms of mass?
Not with this simple model. So that's an interesting
So
question.
if you knew the surface heat flux, could you then convert into a volume?
So I think you have more information, but it's still not close. So you have, for example, you can specify the inflowing TS properties, and then you could specify, for example, and you could also specify the inflowing volume flux. You could then say that there's a certain average heat loss over the winter, and you could compute the total amount of heat extracted. You could then also say similar things about freshwater budget. All of those statements together with what I've showed here is not sufficient to close for the properties of the east rim current and the amount of sea ice that you're left with and then the intermediate water. So that's why I focused on what sets the properties of the intermediate water. If you knew that, then I think with volume, heat and freshwater conservation, you probably could close it.
All right. Steve, you want to go ahead?
Did you say me, Steve?
Yes, Steve, go ahead.
Yes, thanks for that fascinating talk. You, I guess, neglected the freshwater flux into the atmosphere, and is that in fact negligible here?
So my guess is it's probably not negligible, but it's pretty small. I think that in the Eurasian Basin, you're typically melting about, a few feet of sea ice, like 2, 3, 4 feet each year with the Atlantic water in this way. And so I think compared to P minus E, that's probably the dominant term. So actually the Arctic is interesting in comparison to the Antarctic in that respect, because the Arctic gets a lot of freshwater from meteoric freshwater from the atmosphere and runoff. The Antarctic does not. If you believe what I've said in this conceptual model, that wouldn't make a whole lot of difference, at least in terms of the sort of gross features of the TS diagram. So this won't work unless you freeze seawater to make sea ice and then move the sea ice to another place where it's melted. If you're freezing and melting in the same place, although that might affect the stratification of the column, it will not achieve this sort of unmixing of the Atlantic water that I've described.
If that's good enough, we'll move on to Wilbur. Go ahead, please.
Thanks. It was a really fascinating talk, Tom. Thank you. I got a couple of questions, but maybe I should start with the first one, and that is about the intermediate water. And I think you said or showed that if you take phi as 0, that you would basically go straight down that into the diagram. So what is your reasoning that is not a plausible explanation for the temperature salinity structure of the intermediate water?
That's a good question. So as far as I'm aware, there is no observational evidence of that happening in the Eurasian Basin. And so most of my thinking was about that area, and the Nansen Basin in particular. And instead, people think that the intermediate water is formed by dense brine running off the shelves and then mixing as it goes, and then circulating back towards Flam Strait. However, I think that there is no reason in principle why you couldn't have deep reaching convection of the type that you described with little melting of ice, and then you would essentially just cool the Atlantic water. And that probably is more relevant to the Greenland Sea. So in the Greenland Sea, although there's sea ice present, you're essentially there's less sea ice, and so probably some years or at some point in most seasons you run out of ice to melt, and that's not something I've taken into account of, but at that point you would then probably overturn the water column and you'd convect into the Atlantic water. Bert has also speculated that that might happen in the Nansen Basin in the coming decades, which I think is an interesting suggestion.
Thanks. Can I move on to a second question?
Sure.
And is it not also that there's this cutoff at the freezing point, but this very fascinating curvature going upward, right? Is it also something that is being predicted by your model, or?
That's a great question. The answer to that is no. It is not predicted by the model. So the model would, if you were to watch the TS properties of these solutions as they move forward in time, they would move along these black lines. Mm-hmm. Well, I'm almost certain. I haven't done that, but I'm pretty sure once you've set phi sets the angle on the TS diagram in which they move, and then Q just sets essentially the speed in which they will move along that. So I agree that curvature, which is characteristic, is very interesting, and I don't know why it's there.
Right.
And it almost looks like a caustic, actually. Sorry. It looks like a caustic. So that's just speculation. You know, if you had a point here going like that, and then another point further up, which is warmer, going at a steeper angle.
Right.
But don't forget that this TS diagram is water in Fram Strait. So it's possible that in the Nansen Basin, where this model is occurring, the curvature is different.
Right. All right, great. So, well, if I may then do the final question, I really find your model very fascinating. I was wondering, so you keep phi fixed, obviously, but would this also be a model that would be predictive in terms of a polynya formation, for instance?
Yeah, I think so. So, for example, if you went into the unstable region, which is this red piece, then you run out of buoyant fresh water, either because you're melting not enough ice or there isn't enough ice to melt, and then you make the surface layer very deep by entraining a lot of warm water, and then that has a huge heat capacity and a lot of heat, which can then keep polynya open. So yeah, in principle, that could be a mechanism by which you could form, Weddell polynya, for example.
Right. So would it be impossible to have a situation like that in the Arctic, maybe in the future or so?
No, I don't think it's impossible. Exactly. So the numbers to melt ice are between, say 0.5 meter and 3 meters.
Uh-huh.
Well, so those are reasonable numbers, but on the high end here, I mean, you probably aren't melting 3 meters of ice every single spring in the Nansen Basin, and in future there might not be enough ice, or you might run out of ice.
Right.
Yeah, that's Bert's argument that the Nansen Basin might exhibit deep convection like the Greenland Sea used to.
Great. Well, thanks so much. Thanks.
You're welcome.